everyone, welcome to part 3 of chapter 5. Today we're going to continue our talk on gases. We're going to cover topics such as mole fractions, partial pressures, and collecting gas over water. So last time we were using our density calculation, and in it we were able to use the molar mass of a gas to calculate our density. Well, we can also use our density to then go ahead and calculate our molar mass of a gas. So one of the methods, right, that chemists use to determine the molar mass of an unknown substance is to heat the weighted sample until it becomes a gas, and then you can measure the temperature, pressure, and volume of the gas and use the ideal gas law to then calculate the molar mass. Our molar mass, just as a reminder, is always our mass in grams over moles. So if we, at the beginning calculate our grams of our substance and then we heat it up and turn it into a gas, we can use our ideal gas law to solve for our moles, which would be our N, and then we can do grams divided by moles to solve for our molar mass. So here's an example of one of these types of problems. This says, what is the molar mass of a gas if 12 grams occupies 197 liters at 380 torr and 127 degrees Celsius? So we can go ahead and use our Pivnert equation, right, our ideal gas law equation, to go ahead and solve for this. So we have, PV equals nRT. So we're going to use our ideal gas law equation to solve for N. So we'll divide both sides by RT, and we get N is equal to PV over RT. So, okay, N is equal to, and so our pressure needs to be in atmospheres, and right now it's in torr. So we're going to divide by 760, and that will give us 0.500 ATMs. And then our volume we have in liters, which is great, and our temperature right now we have in Celsius. We need to add 273 to get it to Kelvin, so that will give us 400 point Kelvin. So now we can go ahead and plug it in. So our pressure is 0.500 ATMs. Our volume is 197 liters. Our R value is always the same, 0.08206 liters atmospheres over moles Kelvin. And then our temperature is 400 point Kelvin. And if we divide all that up, we'll get that our number of moles, we have 3.00 moles. So now to solve for the molar mass, we can do grams divided by moles. So we have molar mass is equal to 12.0 grams divided by our 3.00 moles. And we will get our molar mass is 4.00 grams, which means that this is helium. So that is how we would solve a problem like this, where we're given grams, and we need to solve for the molar mass. We'll use the ideal gas law equation to solve for moles, and then we will use Pivnert to solve for moles, our ideal gas law, and then we will plug this into grams over moles to solve for our molar mass. One of the main topics in chemistry when we are talking about gases is partial pressure. And the reason for this is that most gases are actually mixtures of gases. And so we can calculate the pressure of our individual gases and then add them all together to get the total pressure. And we can calculate the partial pressure of our gases if we know a couple things. If we know what fraction of the mixture that gas is, then we can calculate the pressures due to each one of the gases and find the total pressure. We can also know the number of moles of a gas, and then we can calculate the pressure due to that using the ideal gas law, and then again, add them all up. But the sum of all of the pressures of the gases in the mixture will equal the total pressure. So the pressure due to gas A plus the pressure due to gas B plus the pressure due to gas C will equal the total pressure. And the reason that we can add them all up like this is because all of the gases behave independently. The gas particles themselves are so small that they're all doing their own thing and they're not really interacting with each other. So each one of those gases will have its own pressure associated with it. And if we add them all up, then we will get the total pressure. And this is called Dalton's law of partial pressures. So, looking at this, we have gas A on the left here and gas B on the right here. And each one of those gases has a certain number of moles. our gas A will have 0.3 moles, our gas B has 0.6 moles. And they each have a pressure associated with that amount of moles. Okay, and right now they are separated, but if we, open that stopcock that's holding them together, and then we'll depress the piston here, which squeezes all of gas A into being with gas B, you'll notice that our total pressure is now 1.5 atms because we've added together the 0.5 and the 1 atmospheres, and we've gotten 1.5. Our moles have also been added together, that 0.3 plus 0.6. And these numbers down here, these are our mole fractions of our gases. And we're going to talk more about that on the next slide. But you'll notice, again, our pressures are always additive, right? So we added our 0.5 here plus our 1, and we got our 1.5. So that's showing you Dalton's law of partial pressures. Okay, so mole fractions. Mole fractions is a fraction that we can calculate, and usually it will look like this. This is the Greek letter chi, and say we were talking about the mole fraction of gas A. The way we would calculate that would be our moles of our gas A divided by the total moles in the mixture. We could also do the same thing for our mole fraction of B. We'd calculate that as moles of B over our total moles. Okay, and our mole fractions should always add up to being 1. You can think about them as being kind of like percentages, except we're not multiplying by 100. So if we add up all of our percentages, normally they would add up to 100. So if we add up all of our mole fractions, then they will add up to 1. That's a good way to check to make sure you've done your mole fractions correctly. But our mole fractions help us to figure out our partial pressures. Because our mole fractions, right, that would be this, our moles of A over our total moles, will also be equal to our pressure of gas A over our total pressure. So we can use our mole fraction to find the pressure that's due to a single gas. So the ratio of our partial pressure to our total pressure is the same as our mole ratio there. So this would be the mole ratio of gas A, or the mole fraction. And again, we can use that to calculate. So if we plug in, this mole fraction here for this, and then we rearrange, right? So if we plug in that, we get partial pressure of A due to our total versus our total pressure is going to equal our mole fraction of A. And if we multiply both sides by our total pressure, we will get this equation here, which is super helpful. If we know our mole fraction and we know our total pressure, we can multiply them together to get the partial pressure of gas A. And then we can know all of our individual pressures due to individual gases. So Dalton's law is that the pressure of a gas mixture is the sum of the pressure of all of the individual gases. And here it says, why does each gas contribute to the total pressure in proportion to its mole fraction? Because again, all of those gases are acting independently. They are not interacting with each other, so we can calculate the pressure due to each individual gas and add them all up because they're all acting independently. It's like they're in there by themselves. They're not interacting with the other gases whatsoever. So let's go ahead and try a problem. This says, find the mole fraction of neon in a mixture of neon and xenon. The mixture has a total pressure of 3 atmospheres, a volume of 8.7 liters, a temperature of 598 Kelvin, and it says there are 0.17 moles of xenon. So all of this information, do you see where it says it has a total? So it has a total pressure of this, a total volume of this, and the overall temperature of this, right? So we can use the ideal gas law, and we can find the total number of moles. And once we find the total number of moles, right, our moles will be equal to our moles of neon plus our moles of xenon. And so then we can go ahead and solve for how many of those moles are neon. So we will use our overall information, right? We have PV equals nRT, and we're trying to solve for our number of moles, so I'm going to divide both sides by RT. So we have N is equal to PV over RT. We have our pressure is in atmospheres, which is great, our volume is in liters, and our temperature is Kelvin. So we can go ahead and just plug all of our numbers in. So we'll get N is equal to our 3.9 ATMs, 8.7 liters, over 0.08206 liters atmospheres over moles Kelvin. And our temperature is 598 Kelvin. So then we can solve for our total number of moles. That would be 0.69 moles. So again, we know that this is total because we have our total pressure and our overall volume, right? Typically, our volume will stay the same and our temperature here will stay the same, but our pressure can change. Our pressure here is what's telling us that it is all of the moles of the gas together. So if we know that we have 0.69 moles total, and some of them are due to xenon, we can go ahead and subtract, right? If we have 0.69 moles total, and we subtract out our 0.17 moles of xenon, then we will get that we have 0.52 moles of neon. Okay, so now we have our moles of neon, and we can go ahead and find our mole fraction. Because once we have our moles, we can do our mole fraction of neon is going to equal our moles of neon divided by our total moles. And now we have all of that information. So we can say, okay, our mole fraction of neon is going to equal our moles of neon, which is 0.52, divided by our total moles, which was 0.69. And if we divide those up, we will get our mole fraction of neon, and that is 0.75. And you'll notice that our mole fractions do not have units, because if you look, the way that we calculated it, right, our mole fraction, our moles and our moles canceled. So our mole fraction is a unitless number, which I know is a little bit weird in chemistry. Most times we're like, we always have to have our units, right? Units give us a meaning, but our mole fraction does not have units. Again, you can kind of think of it as a percentage, but we haven't multiplied it by 100. Okay, it will always be a fraction that's less than 1. So the partial pressure of each gas in a mixture can be calculated using the ideal gas law. So here we calculated the total number of moles, right? And then we found, we used subtraction to figure out the number of moles of neon because we had our number of moles of xenon. But say instead of having our overall pressure, say that we had our individual pressures, right? Say we had our pressure of A or our pressure of B. We could use that to find our number of moles, or we can use that to find our overall pressure, right? We can use these ideal gas laws for overall pressures or individual pressures, okay? The temperature and the volume of everything in the mixture are the same, okay? So that's why in this last problem, I was saying that the thing that's telling us that we are calculating the total number of moles is that we have the total pressure. If it said the pressure due to neon or the pressure due to xenon, right, then we would be calculating the moles of neon or the moles of xenon. But had you had those individual pressures, say instead in the last problem we were given the pressure of neon and the pressure of xenon, we could have figured out our total number of moles by using that to calculate the moles of neon, the moles of xenon, and adding them together. Or we could have added together our pressure of neon and our pressure of xenon to get our total number of moles. Okay, so we can use this ideal gas law in a lot of different ways and just manipulate it to find what we are looking for. So here's another example. This says, find the partial pressure of neon in a mixture of neon and xenon. The mixture has a total pressure of 3.9 atmospheres, a volume of 8.7 liters, temperature of 598 Kelvin, and there are 0.17 moles of xenon. So this is the same problem we were doing before, except now we want to find the partial pressure of neon in the mixture. Okay, so in our last problem, we had solved for the mole fraction of neon. So our mole fraction of neon was 0.75, and that's it, right? We don't have any kind of units. If we wanted, just as a brief digression, had we wanted the mole fraction of xenon, we would take 1 and we would subtract out our mole fraction due to neon, and we would get our mole fraction of xenon. Because again, our mole fraction of neon plus our mole fraction of xenon must always equal 1. Our mole fractions of everything in the mixture must always equal 1. Okay, back to the problem at hand. So we're trying to find the partial pressure of neon. And if you'll remember from an earlier slide, we said that the partial pressure of a given gas can be equal to the total pressure times the mole fraction of that gas. So we have our total pressure here. We solved for our partial pressure our mole fraction in an earlier problem, so we can use that to find the partial pressure of neon. So the partial pressure of neon here will be our total pressure, which is 3.9 atms, times our mole fraction of neon, which was 0.75. And if we multiply those out, we will get that the partial pressure of neon is 2.9 atms. Okay, there's another way that you could have done this problem. When we, before we solved for our number of moles of neon, so had we not gone through and solved for the mole fraction, right? We used all this, we found our total number of moles, right? We did our total number of moles in the previous problem was 0.69. And then we found our moles of neon were 0.52. I think the easiest way to do this problem is to go through and find the mole fraction and then multiply it by the total pressure. But another way that you could have done it was to take our moles of neon here and plugged it into the ideal gas law. So we could have then found, right, we had PV equals nRT, and say we wanted the partial pressure of neon. Then we would rearrange this for pressure, so we would get P equals nRT over V. And now, if we wanted to find the pressure due to neon, we would use our moles of neon instead of our total moles. So we would plug in our 0.52 moles, 0.08206 liters atmospheres over moles Kelvin, times our temperature. Our temperature is going to be the same, no matter if we are talking about partial pressures or total. And then again, our volume is also going to be the same. Nothing changes there. They're all in the same volume because our gas particles themselves are not taking up any space. So then if we multiply and divide all that out, we will get 2.9 atms. So there are two different ways to solve this problem. You could have gone through and found the mole fraction of neon and then multiplied that by the total pressure, which again is what I think is the easiest way to do this. But had you not want to do the mole fraction, you could have said, okay, I have my moles of neon here, and I have that, I have a pressure and a volume and a temperature, so I can go through, I can plug that into the ideal gas law. Sorry, not this pressure, my apologies. But I have a volume, a temperature, and a number of moles. I can solve for the partial pressure of neon using that ideal gas law. So whichever way makes you more comfortable, both ways will work out just the same. Okay, this is one that's actually done a lot in lab. We will collect gas by water displacement, and we actually have a lab on this that we will be doing. And so this is related to it, not the same, but related to it. So what's happening in this problem is that we have some zinc, and it is reacting in the hydrochloric acid. And when our zinc is placed in our hydrochloric acid, it creates hydrogen gas. That's what all these little bubbles are. And the hydrogen gas can be collected, right? It can travel up this test tube and over into this tube. And we have this tube is being submerged in water. And what's happening is that as the hydrogen travels into this tube, it's collecting up here and it's displacing the water, right? It's pushing water out. Okay, but when we collect it this way, it's when the hydrogen is going up into what's called the headspace up here, when the hydrogen's going up there, it's also dragging some of the water with it. So this volume of hydrogen that we are collecting is not just hydrogen, it's going to be hydrogen and some water vapor. So when we're calculating all of this information to find how much gas was displaced, right, how much gas was produced in this reaction, that's how we would do this. We would, react it, and our gas would travel up this tube, and we can use this volume of gas here to figure out how much gas was produced in the reaction. But the gas that's up there is not just hydrogen, it's hydrogen and water. So we're going to use this Dalton's law of partial pressures to figure out how much of that gas is just hydrogen, right? Because some of the pressure and some of the volume is being due to water vapor, and some of it's being due to hydrogen. So we need to subtract out the water vapor so we can figure out the amount of hydrogen that was produced during the reaction. So here is the vapor pressure of water table. This is always going to be provided to you. Please don't go around trying to memorize any of this information, but you're always going to take your temperature in Celsius, and you can use that to find what pressure is being due to water. And you'll notice as the temperature increases, right, as we are increasing temperature, we are increasing our vapor pressure. And this should make sense, right? As we increase our temperature, more and more of the water will start to evaporate, will start to go into the atmosphere or into, whatever headspace we have. And that's because those interactions between the water molecules are going to be less at higher temperatures. So as we increase the temperature, we are going to increase the vapor pressure of water. So more and more and more water will be collected as we do these reactions at higher temperatures. For this reason, a lot of times we'll keep our temperature kind of low during the reaction to try to drag as little water over as possible. But you can always subtract out the pressure of water to figure out the pressure due to just our gas. And in this case, it will be our hydrogen. So here's our example. 0.12 moles of hydrogen is collected over water in a 10-liter container at 323 Kelvin. Find the total pressure. Okay, so our total pressure, right, is going to be our pressure of hydrogen plus our pressure of water, so plus our water vapor. So if we go back and we look at the table here, right, we are using 323 Kelvin. So we need our vapor pressure of water at 50 degrees Celsius here. So that's going to be 92.6 millimeters of mercury. And since we're probably going to do our ideal gas law here, we're going to take our 92.6 millimeters of mercury and we'll divide that by 760 to get our atmospheres. So this is 0.123 ATMs. Okay, and so that's going to be our pressure of water. That's our water vapor. So now we need to go through and find out our pressure due to hydrogen. And if you look, we have moles, we have liters, we have temperature. That looks like an ideal gas law problem. So we have PV equals nRT, and our pressure, right, we're going to solve for our pressure, is then nRT over V. So since we're trying to find our pressure due to hydrogen, right, we need to use our moles of hydrogen here. So it's very important in these types of problems that you know whether you're trying to find the total pressure or the pressure due to an individual gas, right, that partial pressure. If we're trying to find the total pressure, use the total number of moles. If we're trying to find a partial pressure, only use the number of moles of that gas. So here, since we're going to use our number of moles of hydrogen, this is going to come out with our partial pressure of hydrogen. So our partial pressure of hydrogen is going to equal our moles of hydrogen times our ideal gas law constant times our temperature over our volume. So now if we go through and we calculate that, we will get that our partial pressure of hydrogen is equal to 0.32 ATMs. And then to find our total pressure, right, we will go ahead and we will add together the partial pressure of hydrogen plus our partial pressure of water. So we'll say, okay, we have our partial pressure of hydrogen plus our partial pressure of water, and we will get our total pressure. Please make sure that you are following all of the sig fig rules. I've noticed that a lot of us are having trouble switching rules. So in this case, we're doing multiplication and division. So we'll follow the rules, that gives us the least number of decimal places, essentially, or the fewest number of total significant figures. Here we have 2, 4, 3, and 3. So our answer should have 2 significant figures. When we follow the addition-subtraction rule down at the bottom, we're looking at numbers past the decimal point. This has 2 numbers past the decimal point. This has 3 numbers past the decimal point. So our answer can only have 2 numbers past the decimal point. So make sure you're always paying attention to significant figures. Okay. Okay, so we have one last example problem. In this problem, hydrogen is being produced during a reaction and it's being collected over water. This is very similar to a reaction that we might do in class where we're using a reaction. In this case, we're using aluminum and we're reacting with our hydrochloric acid and we're collecting our hydrogen via water displacement. It's telling us that our temperature here, we have 23 degrees Celsius, and the barometric pressure in the room is 742 torr. And it wants to know what volume of dry gas will be collected during the reaction. And this telling us that it's dry gas, that means it wants the volume of the hydrogen alone. So we'll need to make sure that we're not doing anything related to the water when we're doing these calculations. So that's 742 torr. That is the pressure, that's our total pressure. So that's going to be our pressure of hydrogen plus our vapor pressure of water. So to figure out the pressure due to just hydrogen, we can go ahead and do some subtraction because our pressure of hydrogen will equal our total pressure minus the partial pressure of our water. So 742 torr minus our 21.1 torr that was given in the problem, and that gives us 721 torr. And that's going to be our pressure just due to hydrogen. So now we have our pressure of hydrogen, we have a temperature, and we have grams of aluminum. So we'll go through and we'll use our grams of aluminum, right? And there was excess hydrochloric acid, so we don't need to worry about that. We'll use our grams of aluminum to go ahead and calculate our moles of hydrogen gas. We can't use that 22.4 liters equals 1 mole in this case because we are not at STP. Right, we're at 742 torr and 23 degrees Celsius, so we can only use that molar volume when we are at STP. So instead, we're going to use our grams of aluminum to calculate our moles of hydrogen, and then we can use our ideal gas law to calculate our volume of hydrogen. So we have 1.50 grams of aluminum, and we'll use our molar mass of aluminum to calculate our moles of aluminum. And then we can use our mole ratio from our balanced chemical equation to calculate our moles of hydrogen. So for every 2 moles of aluminum, we have 3 moles of hydrogen that are being produced. So we can go ahead and calculate that out, 0.0834 moles of hydrogen that should be produced during this reaction. So now we have our pressure of hydrogen, our moles of hydrogen, and we have our temperature. So we can use our ideal gas law to figure out the volume of hydrogen. So we have PV equals nRT. If we're solving for volume, then we have volume is equal to nRT over P. So we have our moles of hydrogen, 0.0834 moles. We have our ideal gas law constant, 0.08206 liters atmospheres over moles Kelvin. We have our temperature, right? So we have 23 degrees Celsius. We will go ahead and add 273, which gets us 296 Kelvin. And we have our pressure, and again, make sure to be very careful here. It would have been so easy to use this 742 torr accidentally. The key was that it asked what volume of dry gas, which is telling you the 742 torr is including the water vapor, which means that we subtract that out in order to get our pressure just due to hydrogen. So we had, we subtracted it out, we got 721 torr. We'll go ahead and divide that by 760 to turn it into atmospheres, which gives us 0.949 ATMs. So now if we go through and we calculate our volume, we will get 2.13 liters of hydrogen gas. So again, this is a very common problem that we would do in lab. This is a very practical problem and something that will happen all the time. And that is the end of this particular lecture. So make sure to go through and keep working on those Chapter 5 lecture worksheet problems. Do lots and lots of practice. Pay attention to your significant figures. As always, if you have any questions, please send them my way, and I will talk to you guys next time.